Ocean acidification is a process that describes the decrease in the pH levels of the Earth's oceans, making them more acidic. This phenomenon is largely driven by the increased absorption of carbon dioxide, CO2, from the atmosphere due to human activities, primarily the burning of fossil fuels and deforestation. When CO2 dissolves into seawater, it forms carbonic acid, which then dissociates into bicarbonate ions and protons, leading to a reduction in pH. Since the start of the Industrial Revolution, the ocean has absorbed about 30% of the emitted anthropogenic CO2, causing a pH decrease of approximately zero point 0.1 units, which represents a 26% increase in acidity. This alteration in ocean chemistry has profound effects on marine ecosystems and biodiversity. Many marine organisms, such as corals, mollusks, and some species of plankton, build their shells and skeletons from calcium carbonate by a process called calcification. As seawater becomes more acidic, the availability of carbonate ions needed for calcification decreases. This makes it more difficult and energetically costly for these organisms to maintain and build their structures, leading to weaker shells and skeletons. Coral reefs are particularly vulnerable. They are less able to compete with other organisms and are more susceptible to erosion and other stressors, such as warming waters and pollution. Planktonic organisms, which are at the base of the marine food web, are also affected by ocean acidification. Any alteration in their abundance or health can cascade up the food chain, potentially disrupting entire ecosystems. For example, smaller or less nutritious plankton can impact fish and marine mammals that rely on them for food, leading to reduced growth rates, survival, and reproduction. Research indicates that rising CO2 levels can also lead to altered behavior in some fish species. Juvenile fish exposed to increased acidity have shown changes in behavior and sensory functions, which can affect their survival. For instance, their ability to detect predators or navigate to suitable habitats may be compromised. As conditions become less favorable for calcifying organisms, ecosystems could lose biodiversity. Coral reefs, which are rich in species variety, provide critical habitats and protection for many marine species. With the loss of these reefs due to acidification compounded by other stressors, the potential for significant biodiversity loss is high. Ocean acidification can cause other chemical changes in seawater that may have indirect effects. For instance, metals may become more bioavailable and toxic to marine life, while some nutrients essential for primary production may become less accessible. The changes in ocean chemistry and the subsequent impacts on marine organisms have significant economic implications, especially for communities reliant on fisheries and marine resources. Shellfish aquaculture, for instance, can be severely affected as shell formation for species like oysters and mussels becomes more difficult. To address ocean acidification, efforts are underway to reduce CO2 emissions globally through the adoption of renewable energy sources, improved energy efficiency, and carbon capture and storage technologies. Meanwhile, conservation efforts are focusing on protecting marine habitats, monitoring ocean chemistry, and supporting research into species resilience and adaptation. Ocean acidification poses a serious risk to marine ecosystems around the world. As a subtle and pervasive process, it challenges both the resilience of our oceans and the species that inhabit them. It's clear that urgent actions to mitigate CO2 emissions and protect vulnerable marine environments are essential for preserving the biodiversity and services our oceans provide.